All right, good morning. Let's continue with chapter 3, discussion of inductors and capacitors. The homework is now, I changed it over the weekend because we hadn't covered enough material, so it's due on Thursday. Some of the homework questions are conceptual, some of them are problems. You will be able to answer most of those questions based on the previous lecture and then today's lecture. And then again, I will try and cover example problems today. If not, they'll be finished by Wednesday. But do not wait to get started on the homework. The reason I have opened up all the homeworks in advance, again, I'll repeat, is that students can get ahead of the homework. Some questions you can, if the topic or the chapter is spread over like 2 or 3 or 4 lecture classes, then you can start, at least a portion of the homework as we cover the material in class. Okay, so do not wait until the end to begin the homework. All right, so this notebook. Okay, there we go. All right, so we stopped here on the physical construction of the inductor. So make sure. And did I cover this slide? Okay, all right. I'm wondering I didn't have notations on here. Okay, all right. Time at which we begin analysis. So this was the standard VI equation. And you will see when we get to capacitors that the structure of this equation is exactly the same for both inductor as well as capacitor. Okay, so again, repeat, our job during circuit analysis is to determine the unknown quantities. Unknown quantities in this case are the voltage and the current, right? So these are the equations that we would use for inductors and capacitors. So for an inductor, we always talk in terms of the input current, and then we find the voltage when an input current is applied to an inductor. So V is equal to L di over dt. When we get to capacitors, we talk in terms of applied voltage, and where we find the resulting current. So I is equal to C dV over dt. Exactly the same structure. Okay, basically di over dt indicates that all the quantities now are time dependent, right? Energy storage devices, energy cannot transfer in an instant. It takes a certain amount of time, and so the quantities are time dependent. Quick word about notations. Here is simply noted as V. We know we are talking about an inductor, so we don't have to have a subscript notation. Sometimes you will see a subscript notation as VL. Sometimes you might also see something as V of t, meaning voltage as a function of time. You might also see VL of t, simply indicates is the inductor voltage as a function of time. So again, in this case, the subscript notation is simply indicating which component that voltage or current is referring to. Okay, when we get to capacitors or resistors, we might have VR, VC, IC, IR. That subscript is simply noting the component under analysis. Okay, so all kinds of notations will appear. It would be your job to recognize, what component it's referring to. Okay, so if we are given the voltage and we wish to find the current, then we simply integrate both sides and we end up with this equation. Simply integrate the voltage between a certain time period, t0 to t. The limits of the integration simply specify the time at which we begin analysis and the time at which we end analysis. Again, it could be a large time period, and we might be analyzing a small portion in the middle. And so then t0 and t will have specific values. The 0, the subscript 0, is simply indicating the time at which we begin analysis up to the point where we stop our analysis. Okay. So inductor voltage V is L di over dt. What if the current is constant? If I is constant, then di over dt, mathematically, we are expressing it, right? Mathematically, we say di over dt would be equal to 0. Conceptually, Current is passing through, energy is being transferred to the inductor. At a certain point, the inductor is charged fully. Bucket is completely full. At that point, the inductor behaves like a short circuit. And when we say constant, meaning it doesn't change its value with respect to time, meaning it is DC. So constant voltage or current indicates that we're talking about DC, right? DC is simply a flat line. If you plot the value of the voltage or current with respect to time, then the value is completely constant. It's a flat line. So if you apply DC to a capacitor or inductor, then the behavior changes after it gets fully charged. For an inductor, once it reaches full charge, it acts like a short circuit. Think back to the beginning of last class lecture. I said in chapter 3, we'll look at the generic equations that govern the inductor and capacitor voltage and current. In chapter 4, we will specifically look at just the charging phase and the discharging phase, where the energy is being transferred in and out of these devices. Okay. So when the energy is being transferred into the capacitor or inductor, we refer to it as being charged. And when the energy flows out, we say that they are being discharged. Okay. And again, that's a discussion for chapter 4, but I'm letting you know in advance. When energy is being transferred into these components, we refer to them as being charged because it's building up and energy is being built up. And when it flows out of these components, we refer to it as being discharged. Now, steady state simply means that it has reached a full charge or a full discharge. In this case, since the energy is flowing in, it's reached full charge. Fully charged, and then current flows through it freely. There is no opposition to the change of current. Okay. So for DC or steady state behavior, inductor behaves like a short circuit. All right, think on that. Let me know if you have any questions. Any questions? Okay. I'll jump ahead for a single note. So when we apply AC, AC means the value of the voltage or current changes with respect to time, right? So the property of an inductor or capacitor is such that, well, let's talk about inductor right now. The property of an inductor is such that when you apply a DC voltage or current starts flowing through it, magnetic field is set up, energy is being transferred and stored in that magnetic field, right? At a certain point, that magnetic field and the inductor reaches full charge. It can store as much energy as its capacity is, as much capacity is available. After that point, the current flows freely, meaning there is no opposition to the flow of that current. It acts like a short circuit. After this point, or actually even before that point, what happens is the magnetic field that is set up, it creates a back EMF, or it creates a voltage that has a polarity that is exactly opposite to the current that is actually flowing through the circuit. Okay, again, I'm trying to stay on this side and not jump into the physics. So current flows to the inductor, sets up a magnetic field. That magnetic field gives rise to an opposing voltage. That opposing voltage will resist any change in the value of the incoming current. Notice it will oppose any change in the value of the current. So if the current remains steady, meaning if it's DC, there is no opposition. But if it's AC and the value keeps changing, then the inductor will actually oppose that change. So this is a very important point to keep in mind when we get to chapter 5, AC analysis. In AC analysis, the value of the voltage or the current keeps changing constantly, right? And so the inductor's magnetic field gives rise to an opposing voltage that opposes any change in the incoming current. All right, think on that and let me know if you have any questions. Any questions? Okay. Power, electrical power is simply the product of the voltage and current. So we simply plug in the values for voltage and current in there. Current, of course, might be known to us because that's the input. We simply plug in the voltage equation, L di over dt, and we obtain this equation. And power, of course, energy is the time rate of expending energy, meaning the rate at which the work is done. Energy, or W work that is being done, is half Li square. Half Li square. And again, you don't have to memorize any of these equations. There's a summary slide at the end of this chapter. And again, it's open book, open notes. So you can refer to it anytime you want. Okay, yes. No, this is the value of the inductor. Okay, yeah. So Li square, the inductor, and the inductor current I. Yeah. Uppercase typically would be referring to a component in general. Okay, capacitor. I will explain a little bit of the physics of how the capacitor works, but after that point, I will tell you to leave the physics on the side and think in terms of just engineering. Okay, so capacitor is nothing but two parallel plates separated by an insulating material. Okay, it is exactly the same as well as opposite of an inductor. Many of the equations are exactly the same. The structure is the same, except the values are changed. Not the values, the variables. Okay, so we had the voltage equation for an inductor, that becomes the current equation for a capacitor. So parallel plates separated by a dielectric layer, meaning two conductors separated by an insulating material. You could take the two palms of your hands and put them together. They are separated by air. Human body is a conductor, right? So if you measure the capacitance between your two palms, you will obtain some capacitance. Now, it'll be too small to be measured reliably, but it's present nonetheless. And again, as I stated, right, you could take any wire, any cable. It has resistance, capacitance, and inductance. Especially like a cable will have 2, 3, 4 multi-strands going through it, right? A USB cable, a standard USB cable has 4. Okay, plus minus in the data cable, at least 3, if not 4. Okay, there's data plus, data minus, plus 5 volts and 0 volts. So there's at least 4 in there. Sometimes if it's just a charging cable, it might just have 2. But all of those conducting wires have to be separated by an insulating material, right? So you have 2 pairs of conductors separated by insulating material. Across the entire length of that cable, there's a capacitance that you can measure. But again, that capacitance does not rise to the level of interference of that functionality. So in this case, as you see here, you have 2 plates. Both of these are conducting plates. Electrical conductor, and it's separated by an insulating material. Now, of course, this is enlarged just to show the concept. In real life, the distance between them is very, 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 very small in microns, right? Very small, very tiny. The symbol for a capacitor is simply two parallel lines of the same length. Okay, two parallel lines of the same length. Sometimes you might have a concave symbol like this one. If there's an arrow, through that capacitor, it means the value is variable. And this is true of all components. You could have a resistor that has an arrow through it. It means it's a variable resistor. You can have an inductor that has an arrow through it. It also means the value is variable. So an arrow through a component simply means the value is variable. Now, capacitors do not have polarity. Like resistors and like inductors, they do not have polarity, okay? With the exception of one specific kind of capacitor. These are the electrolytic capacitors, and they do have polarity just because of their physical construction, okay? So these electrolytic capacitors are basically a conducting film that is coated with a gel-like substance. And then you roll it up. Once you roll it up, you now have two conducting plates separated by a very thin layer of insulating gel. When you roll it up, the gel is activated when you apply voltage to it in a specific polarity. Okay, and the gel acts as a insulating material. And so those are the only kinds of capacitors that actually do have polarity. Most capacitors do not. Okay, they do not have any polarity. So how does it work? Let's say you have a capacitor, you connect it to a voltage source, right? At the beginning, the capacitor does not have any charge across it. The voltage measured across that capacitor is 0 volts. Okay, completely discharged. There is no energy stored in that capacitor. Then at some point in time, the switch closes. Remember from chapter 1, switch opening and closing. So switch closes. As soon as the switch closes, the voltage source is connected to that capacitor. This voltage source has polarity plus at top, minus at the bottom. Opposites attract. So the electrons at one end of that capacitor are attracted to the positive terminal of that battery. They start moving in a counterclockwise direction. At the other end, you have the negative terminal of the battery that repels the electrons and pushes it towards the other end of that capacitor. So you have a constant motion of electrons in a counterclockwise direction. Does that make sense, right? Slowly but surely, charge starts to build up. At the top plate, because the electrons are moving away from the plate, it leaves behind an equal but opposite positive charge. An electron moves away, that leaves behind, in semiconductor physics, we refer to it as a hole. Electrons and holes. When an electron moves away, it leaves behind an equal but opposite positive charge. And so you have a buildup of positive charges on the top plate. You have a buildup of negative charges on the bottom plate. When you measure the voltage across that capacitor, it'll slowly start increasing. That capacitor voltage, after a certain point in time, reaches the value of that battery. So VC will equal the voltage source VS. At that point, there is no more charge imbalance between the battery and the capacitor. There are no more electrons that will be attracted to the positive or the negative terminals, and it stops moving, stops flowing. You can now take the capacitor out of the circuit, and if it's an ideal capacitor, it'll act like a battery storage, right? It'll hold that charge across it indefinitely. At that point, we say this is a fully charged capacitor. Fully charged capacitor. Okay, fully charged capacitor. When electrons flow through a circuit, we say that current is flowing, right? Current is flowing. Current always, we take it as the opposite of the flow of electrons. So the electrons are flowing in the counterclockwise direction. We say the current is flowing in the clockwise direction. And so in this circuit, in this figure, we say the current is flowing in the clockwise direction, which again satisfies the passive reference configuration. A power supply, the current always goes from minus to plus. And capacitor, passive component, will have plus up top, minus at the bottom. And so current through this capacitor is going from plus to minus. So there's a lot of information to take in. So let's take a longer pause while you think over all of that. And then let me know if you have questions. Yes. So the question being asked is, why is the flow of electrons counterclockwise? Well, it's because the voltage source has a plus up top. Positive charge attracts the negatively charged electrons, and so they are flowing in a counterclockwise direction. And there are a couple of other important points that I will make after. All right, any questions? Yes. That's a good question. Eventually, yes, it will. So the question being asked is if there are resistors in the circuit, which we will look at circuits that do have resistors, then does the voltage across the capacitor equal the voltage across the source? The answer is that it depends on the source and the circuit configuration, but in general, yes. Okay, any other questions? Okay, so at this point, I will tell you, leave the physics on the side, right? The movement of the electrons and everything on the side. We just described the capacitor as two conducting plates separated by an insulating material. And I said the electrons move and charge accumulates on the two plates, top and the bottom plate. Are they crossing through the capacitor? Just logically speaking, it's an insulating material, so it doesn't allow anything to pass through, right? So the answer is no, it doesn't. Nothing actually flows through the capacitor. And again, as I said, leave the physics on the side. Think of it in terms of electrical engineering circuit analysis. We still state that the current is flowing through the capacitor. Okay. So when you think of the capacitor circuit, when you look at a circuit that has capacitors, always think of it in terms of like a resistor or an inductor where the current is actually passing through the capacitor. If you try to understand it from the physics side of things, I've seen students get confused a lot. So again, as I said, leave the physics on the side. The movement of the electrons and the positive charges and accumulation of the charges, leave that on the side for a little bit until you actually reach a higher level of understanding. Okay, so understanding that is good, but right now the primary purpose is you should know how to perform circuit analysis, in capacitive circuits. So think of capacitors similar to resistors and inductors where current is actually flowing through the capacitor. Okay, it does not actually flow through the capacitor. but we refer to it as capacitor current. We say current flows through the capacitor. So that's kind of like, confusing to a lot of students when they study this for the first time. So again, as I said, it's good to understand the physics and the engineering side, but for now, for your understanding, if you're first starting out, leave the physics on the side and think only in terms of circuit analysis. So current does not actually flow through the capacitor, but we refer to it as capacitor current. We always say current flows through the capacitor, voltage across the capacitor, energy stored in the capacitor. Okay, it's a constant change. All right, questions about that? Okay, so then remember what I said, that at one point, VC will equal VS, capacitor becomes fully charged, no more electrons will flow through. If electrons are not flowing through, that means current has come to a stop. I is equal to 0, voltage has reached maximum. That means, I'm going to skip ahead, and I'm going to talk about this. That means capacitor acts like an open circuit because no more electrons are flowing, current stops. We say capacitor behaves like an open circuit when it reaches full charge. So steady state again is when you apply DC and it reaches full charge. Okay. DC or steady state behavior. It reaches full charge. And then similar to the inductor, if you apply AC, there is constant change in values. Okay, constant change in value. So similar to an inductor, a capacitor, the stored energy will oppose any change in the applied input voltage. So the faster it changes, the higher, not higher, but the more current that would actually flow through the circuit. Remember, when there's a constant applied, capacitor reaches full charge, acts like an open circuit. So if it changes, what happens when it changes? You now have plus minus this way, and then it changes plus minus. The capacitor starts again, but in the opposite direction. So the electrons start flowing in the opposite direction. Okay, so again, when you apply AC, the behavior is different. Okay, and that's again an important point that we will look at in detail when we get to chapter 5. We look at capacitor equations later on. There's one more slide. I just want to do that because that's one of the problems that's asked in the homework. So you can do the conceptual based as well as this one right here. And it's not too difficult. There's no examples that I do on this. Inductors add up the same way as resistors. Capacitors, the opposite of resistors. Okay. If you have inductors in series, you simply add them up. If you have capacitors in parallel, you simply add them up. Parallel capacitors, it's simply C1 plus C2 plus so on and so forth. Inductors in series is simply L1 plus L2 plus so on and so forth. Okay, that's one of the questions in the homework. There's no example that I do for this. Again, it's rather straightforward. And then there's a summary slide of equations right here. And the next class, we'll look at the example problems. So again, go ahead and get started on the homework. It's not due until Thursday, but again, you have plenty of time to get started on it. All right, I will see you all on Wednesday. Let me know if you have any questions. I'll be in my office later this afternoon. Yes. Yeah.
I don't know if I like